Right. So in terms of what we're going to do today, I think I need to reread this section. So I'm going to start from the object detection section.
Okay.
And reread it till the end.
Yeah.
And then if we give it, say, 45 minutes, at say 10 to 7,
okay.
We'll catch up and we'll go through it, because there was a few, I mean, last week I was going through it a little bit and there's one or two bits which I didn't really understand. And I kind of slightly, went fast through them so people wouldn't notice. But since the two of us, we can go through it. Well, what do you think?
Yeah, absolutely. Yeah. I didn't get a time to go through, but I was, before coming to the class, I was going through, and then still I don't grasp the everything. So definitely it's a good idea if we go through a couple of cycles,
Yeah. So let's do that then. We'll catch back up at 50 minutes past, and we'll start at the object detection section.
Okay.
Okay. Speak to you in a bit then.
Cheers.
All right. Bye.
Bye.
Oh, hey guys.
Hello.
Hey Arthur, how's it going?
Fine, how are you?
Yeah, pretty good. Okay. I might be relying on some of your understanding of aspects of this because I'm not 100% convinced about some of what was actually said in this particular sections that we've got here. But yeah, we'll see.
If I can help, I'll do it, but I'm also like not super familiar with object detection.
Yeah. Yeah, it's more generically. I mean, some of the claims that are being made about the amount of computations needing to be done. I'm not sure. I'm a little bit dubious of it, but we'll see. Did you manage to read that paper you were going to read, the unsupervised thing?
Oh, not yet. I'm going to do it today or tomorrow morning.
Yeah, I was lucky that the one that I chose, and this was the template one, the RASA paper reading group. It's a lady called Rachel Tapman who does that on YouTube. She actually read that paper. So I just listened to her. She did it in 2 different sessions. But it was interesting to get her perspective because she's obviously, a fully trained PhD neuro sort of linguist who works for RASA. They're basically a chatbot company. So yeah.
When does she read these papers? Is there any fixed time, or she announce it first?
She announces it first. So she normally does it on a Friday afternoon at 5 p.m. But the videos are on YouTube. So I can't make it like Friday 5 p.m. But yeah, I just watch them afterwards on YouTube. So
Okay.
if you search YouTube, RASA paper reading group,
Yeah,
she's read a few interesting ones.
Yeah, I know her. From the day of the Kaggle. She used to be Kaggle before joining RASA.
Oh, right. Yeah. Interesting. Yeah, I mean, as I said, I'm learning more and more, but obviously, every time I listen to her, I just realize how little I know. Yeah, because obviously, she's been studying linguistics for a very long time, having done a PhD as well. So yeah, cool. Right, guys. So yeah, let's start this section. As I said, I'm still not 100% certain I understand it all, and there's aspects of it which I'm not sure 100% I agree. But anyway, let's get this going. So I think we have done this section before, but we'll go through it anyway. So so the task of classifying and localizing multiple objects in an image is called object detection. So yeah, detecting objects in an image. And until a few years ago, a common approach was to take a convolutional neural network that was trained to classify and locate a single object and then slide it across the image. Yeah, so basically, yeah. So let's say this was this CNN, that particular size one. You just scanned the whole image sort of multiple times. And the output would be whether or not there was an object in that region or not. And then the output of that would be a huge number of banding boxes potentially because the same object would be detected multiple times by this procedure. And then they have a little kind of algorithm which helps to sort out those all those banding boxes. And the algorithm basically is, first step is you choose the banding box with the highest objectness score. And then any that are overlapping with it more than a certain amount, and that's kind of a hyperparameter, those banding boxes are just dropped because obviously this banding box where recovers those. And then you kind of repeat that whole procedure, I guess, looking at the next highest banding box that is left, and then getting rid of all of the intersecting banding boxes with that, and then redoing it until you don't have any more banding boxes to do. And the final result is basically a whole load of objects detected in a scene. Is everybody okay with that one? Or is there
question? When we say we slide the box, what does it mean? Is it mean like we do the filter? We go through a filter?
Yeah, okay, so right. So the idea is that we're dealing with a convolutional neural network of some sort. Yeah. but it's only of a certain. It only handles a certain size. And the reason it handles a certain size is because it's got that dense layer at the end, which gives you that objectness score and the on whether or not there's an object there or not. So let's say that this convolutional neural network only really works on images of 10 by 10. Yeah. And then let's say this image is like 224 by 224. Well, you start in the top left, and then that'll be the first iteration would be to looking at 10 by 10 there. And then you slide it to the right a little bit, do another 10 by 10, slide it right a little bit, do it again. And you're going to have to do this hundreds and hundreds of times, obviously, because it's going to walk the whole image like pixel by pixel.
So one second. So you have a model which looks only 10 by 10.
Yeah.
But now your image is 224 by 224.
Yeah.
So you're going to take a portion of your image and send it across to this 10 by 10 model.
Yeah.
And then you're going to slide one pixel, then you go to the next pixel and then take, let's say, and then you take that portion of a picture and then send it back, send to 10 by 10. So you keep on moving your image in chunks in a model which accept a small portion of an image. Is that correct?
Yes, that's my understanding. That's what's happening, is that your neural network can only cope with a certain size image, and so you use that like as a window on the underlying image, and you slide it across. And at each stage, you're told whether or not there is an object in that region or not.
Yeah.
And then over a period of time, you get dozens and dozens and dozens of those. And then you've got this clever algorithm which kind of sorts out to get rid of all the duplicates, that way you detected the same thing again multiple times because you were only moving one pixel at a time to the right or one pixel at a time down to the left. Yeah, the bottom. Sorry.
What's the algorithm? So let's say we have an overlapping. He mentioned what we are looking to reject it, or we already say, oh, we already know about it.
Yes, yeah. So the output of the network is an objectness score and a bounding box within the region. So the idea is that it's not that the whole 10 by 10 is your bounding box. The convolutional network is going to output you whether or not there is an object there and what its bounding box is within the current image.
Mm-hmm.
Yeah. And so the output is going to be loads and loads of bounding boxes and a score for the image, whether or not the image is there.
Okay, yeah. And
then, so then the idea is that not all of those scores will be the same. Some scores will be higher and some scores will be lower because maybe, for instance, that bounding box there, it's got a very high rows detection object, whereas one slightly further to the left, maybe it's only got a small part of it. So it still gives you the fact there's an object detected in our rows, but the score is not as high in theory. Yeah.
Yeah.
And then what it does is, sorry. Yeah.
How does the model knows the relativeness that, okay, we are looking at the same flower, we are not looking at some different flower?
I guess it depends on how you've trained it. I mean, they've only given the description where that's what you get. But I guess if when you're training it, you know where the exact bounding box is of the of the rows, and at that score, obviously, you probably want the probability as 1. But if the overlapping of your of your image is only partial, then you can give it a low. Yeah, it all depends on the training as to how you've trained it to recognize that thing. Yeah.
Yeah, but the only confusion I have is you want to get, let's say, the flower you're pointing to. We have 3 flowers in the same image of exactly the same size, but on 3 different locations.
Yeah.
So I mean, like, we want to get rid of a bounding box, overlapping bounding box, only on a first image, not the second, because then so the relativeness of the bounding box for the image 1. That's what I'm trying to get into. How do I know that this is overlapping?
Well, the overlap is by the output of the banding box, yeah? Because as you slide it across,
Yeah.
you'll get different banding boxes and different scores, yeah? Because as far as I know, each particular convolutional neural network is only give one objectness score and one banding box.
Yeah.
So the fact that you've got two there, there's a big thick one and a little thinner one.
Yeah.
That's probably that the current one is this thicker one, because this is. But when the window was maybe a little bit further to the left, you got this one, but it had a slightly lower score on it.
Yeah.
Yep.
The only I still have a confusion that I understand the you're gonna have the flowerness will be high on the thicker lines and then lesser on the smaller lines. However, the confusion I have is the relative of a thicker line to the other, like the smaller lines. So how does the model know that, oh, this is the overlapping? So I should reject. If you have multiple images in a same picture, so how does the model decide that this is the overlapping one and this is not the overlapping one?
Okay, so let's take a step back again then. So this convolutional network that we're using here, it only detects one rows, yeah? So it gives a score for whether or not there is a row within the current image and the bounding box of that rows, yeah? So are we agreed so far that at any particular point, it will only give one of these guys, yeah?
Okay.
So, and so let's say that it was kind of, this network was sliding across. And then I guess at this point, when it was kind of maybe over here, it found this banding box, this, the one that's kind of this slightly thinner one, and say there's a rows here. Yeah. And then later on, when this window was actually maybe down here a little bit, it found this other banding box, the second one. Yeah. So, and then when the whole network has finally finished, then what you've got is a whole load of banding boxes and scores. Yeah.
Okay.
So that's the final output. Yeah.
Yeah.
So now what you've got to do is somehow sort all of that stuff out, because the same object is probably having been detected lots and lots of times as the window was sliding across.
Yeah.
Okay. So the algorithm they use is, first of all, because you got a score for every banding box that you got, you choose the one that's the highest one, the one with the highest score.
Yeah. Yeah.
And then what you do is you look at all the banding boxes that intersected with the one that was the highest one.
The highest one, yeah.
Yeah. And then you define some notion of that they intersected a lot. And, that's a hyperparameter. But let's say if the intersection was more than 30% or something like that. Yeah.
Yeah.
Then you delete those from your set of banding boxes that you consider. So basically the idea is that because this thin one is intersecting with this other one more than 30%, if this one had a higher score, that one would be removed from your data set. So you would be left only with this one, the one, the square one. Yeah.
Yeah. Got it.
And then you sort of apply the same thing to all the other banding boxes. So the idea is then you find the next one, which is the highest one, and then get rid of its intersections that you shouldn't ignore. And then you do it again and again and again until you're left with basically none that you have to consider, in that there's none that are like overlapping too much. It might be that there's still some that overlap a little bit, because there might be, like, some weird banding box over here somewhere. But that's kind of like a weird case. But that's the idea, is that eventually what you'll end up with is just the banding boxes which had kind of like the highest scores, and any that overlapped with them with slightly lower scores were removed from your set. Okay.
Yeah. Thanks.
It's an interesting question how they trained it, because obviously, this neural network's only being trained that there is a rows in here, and this is the banding box for it. So I guess they probably annotated the image with where a road was and its banding box, and where a rows was and the center of it, I guess. Let's say, the center of the rows is here, and this is the banding box around it. And then as they were sliding the thing around, they could somehow compute, what the bounding box would be and the score for it based on maybe how much of the bounding box was within the image. I don't know. As I said, I'm just guessing that that's probably how they trained it. But it's an interesting question how you train a neural network, a CNN like this, to recognize roses and their bounding boxes. But they don't really describe that in this section, how they did that. But the other thing is they're saying, well, basically, this is horrendously expensive in terms of computation, because the same parts of the image are looked at, dozens and dozens of times, because you're only moving it 1 pixel at a time to the right.
Yeah.
So basically not very practical, approach to do that. But fortunately, people have found a better way of doing it. So, and this is where it says, fortunately, there is a much faster way to slide a CNN across an image using a fully convolutional network. Yeah, so this is a bit where I didn't 100% agree with you, because he seemed to imply that just because you used a fully convolutional neural network, this would make it hugely more, efficient. But basically, with a convolutional network, all you're doing is you're replacing, each one of these guys with basically the number of channels. So let's say this, the very first layer had 50 channels with a 7x7 convolution or 10x10 or whatever. Well, that's looking at the image 50 times. And it's sliding it as well, depending on what the stride is, maybe 1 pixel to the right and then recomputing it, 1 pixel to the right and recomputing it. So, I mean, yeah, sure, it is more efficient in that probably you don't need as big here where you're having to look like a huge thing because the bounding box has to be within this region. But I wasn't fully convinced. I mean, I could say that it was going to be more efficient, but I couldn't see that it was going to be much faster. I don't know if you guys disagree with that. Maybe it is much faster, but I didn't think, the number of channels that convolutional neural networks normally need, that it was going to be really a lot faster.
Yeah, I agree. I think that's what we started the CNN on, the premises that this is a fully convolutional. It's not the deep layer. So what would be the fully convolutional?
Oh, okay. So the Folio Convolution is the next section. This is basically replacing the dense layer at the end with another convolutional network. With a convolutional layer. So yeah, maybe it's just that the kernel sizes are really small, like 3x3, 2x2, 5x5, and not by 100x100 like we've got here probably in that image.
Yeah, but then I think what he said initially when we moved from the deep to convolutional network, because the multiplications are so less as compared to on the deep neural network, you have a node, you have like a multiplication, or like you have to maintain the weights on every single node. But once you push the CNN on it, those calculations drastically goes down.
Yeah.
I think, so that's the convolutional part. So I think fully convolutional would be maybe a little bit more processing, but definitely less than the deep neural network.
Yeah, maybe he's right. Maybe it is much faster. I wish he'd slightly quantified it, saying if you had a 224 by 224 image, and the convolution was operating at that size, this would need n number of computations, whereas a fully connected network would need, I don't know, 10% of those calculations. But yeah, interesting. Okay, so let's move on to this fully convolutional network. Yes, so basically. In this paper by Jonathan Long, they had a look at what exactly it was that the dense layer at the end was doing. And they noticed that actually the calculation that the dense layer was doing was actually very, very similar to what a convolution would do if it was of a certain kind of configuration, like a certain size and stride. And so they proposed actually doing away with the dense layer and using a convolution instead. And one of the nice side effects that this has is that now there's no kind of hard wiring of the sizing of the image they can operate on, because dense layers always have like an input size and an output size. And if the input size doesn't match, what they're being placed on top of, then obviously, the whole thing kind of falls apart. Whereas the nice thing about convolutional layers is that no matter what you operate on, you will get a certain type of output. Now, there's still the question mark of what you do with that output, because, okay, fine, the network's not going to fall over because there's a mismatch in sizing. But the output shape highly depends on what the input shape was into the whole network. So, you haven't gotten rid of the problem altogether. But it's interesting that, in that, so that's what I slightly take away from it. I don't know, what do you guys think about this notion of getting rid of the dense layer and replacing it with a convolution layer? Did you understand how that worked?
Yeah, kind of, because I think it's you remember that bottleneck layer where when you have a kernel size of a same size of whatever length and width of your feature. So
Yep.
all you're doing is you are reducing every feature to just a one pixel, one number.
Yeah.
That's exactly what he is doing here.
Yeah. Yeah.
Yeah.
So it's so here they're going through an example of it, of converting that. So instead of it being flat, so for example, suppose we'd already trained a convolutional layer for flower classification localization. It was trained on 224 by 224 images, and it outputs 10 numbers. 0 to 4 are sent through the softmax function, and this gives the class probabilities. So, okay, so you're selecting 4 classes. Output 5 is sent through as the logistic activation function, and this gives the objectness score. And output 6 to 9 do not use any activation function, and they represent the bounding box's center coordinates as well as height and width. We can now convert its dense layers to convolutional layers. In fact, we don't even need to retrain it. We can just copy the weights from the dense layers to the convolutional layers. Alternatively, we could have converted the CNN into an FCN before training. So if you knew how the exact shaping of the convolutional and the dense was working, you could just copy what it was in the dense layer, because the calculation is exactly the same. Okay. And then they've got this notion of so if the output was a 7x7 feature map where the network is fed 224 by 224 image, if we feed the fully connected network a 448 by 448 image, then that final, your bottleneck layer will now be 14 by 14, because if the 224 was compressed down to 7, then if you started with 448, it will only get compressed down to 14 by 14. Since the dense layer output layer was replaced by a convolutional layer using 10 filters of size 7x7 with valid padding and stride 1, the output will be composed of 10 features maps, each of size 8x8. This is the bit which I didn't really agree with. I mean, if it's 14 by 14 and your convolution is 7x7, then I would have thought you would have finally ended up with 7x7, because I can't see how you can get 8 into 14. But maybe I'm not understanding how the maths of this works. But I mean, he claims that the output is 8x8, whereas I thought it should be 7x7.
I seriously don't understand this whole calculation. That's exactly the question I wanted to ask. That when you run the 7x7 on a 14x14, how does you end up in an 8x8? And then you see the calculation he has done, like 14 minus 7 plus 1. I have seen this calculation somewhere else as well. So he has done it. This is like few times, and this bit I don't understand myself as well. It's a quite important part though.
Yeah, I tried looking for it earlier on as to where it was that given a certain input and a certain size, what the size of the output was going to be if the stride was 1 and if it was invalid, if it was in valid mode. But even kind of mentally picturing it, 7x7 on a 14x14. So first time it'll be on 1, second time it'll be on the second column, third time it'll be on the third, and then fourth, fifth, sixth, seventh. Oh, it is 8. Yeah. Okay, so yeah, so imagine here you've got 1, 2. Yeah, let me see if I can do it. Have I got Libre Excel?
So when we say the padding is valid, that means it's gonna put one.
so well, valid is that it will not mess with it at all.
So okay, so it's gonna keep moving from first, and it will stop once the last kernel's cell map with the last pixel on the right hand side.
Yeah. So okay. So 14 by so if a 1, 2, 3, 4, 5, 6, 7, and then 1, 2, 3, 4, 5, 6, 7. So that's 14 by 14. So
Yeah.
the idea would be the first, the very first kernel 7 by 7 would be here. That's 1.
Yeah.
And then number 2 would be here.
Yeah.
And then number 3 would be here.
Yeah.
And then and the 7 by 7 would go up to so once you're on 7, up to 7 would only go up to 6.
Okay.
So this has to gone from 1 to, so you've done 7 by now, and it's only when you go to the 8th one that you actually go all the way to the end. So yeah, okay, it is 8 by 8. Did you get that?
14. Yes. So okay. And then if you go back to the I get it. What you just said there. So the calculation he has done is 14 by 7 plus 1.
Yeah.
Plus 1. So he's saying, okay, this is your source. That's your kernel size. You minus it, and then you always add. I guess you always add 1.
Yeah. So I guess if you just include the first bit, that's the 7 by 7.
Yeah.
And then the add 1 is the fact that you can do one final one from this bit. Yeah.
So okay. So if he had the padding as what's the other name for a padding?
But the other padding is same.
Same. So
yeah.
if you do the same, then it's going to be 14 minus 7 plus 2.
No, because this one doesn't need padding, because this fits, doesn't it? Because
no, if the padding is same, it would add however much you need of padding to keep this size the same.
Oh, okay. So we did have to add like 6 paddings, so that you would still get that column's worth of data.
So you're saying it keep going until your kernel start from the last pixel?
It all depends whether you could add the padding over there as well, I guess. It all depends on how it pads it, whether it pads it only at the end or around it.
Both sides. So you have like probably 3 here and 3 here.
Yeah.
And it would result in 14 total.
Yeah.
Okay, so we are saying, just to get me my mind right, that means like if the padding is same, so it's going to add 6 more pixels in there.
Yeah.
Okay. So in a sense, then our calculation would be 14 minus 7 plus 6.
So then that would be that would really end up being what would the final result be?
Yeah.
It would be 14 plus 6. So that would be a 20 by 20, I guess.
Why 20 by 20?
Well, the final result would be 14 by 14, so we can like go this way. So we have 14 minus 7.
Yeah.
And then this plus 1 is due to the fact that like you always can do at least one convolution if you have the same size of an image and a kernel, and then you go from that you can go like recursively by adding more if your picture is bigger than the kernel. And then we add this 6 in the end, so we have like 14 minus 7 plus 1 plus 6, which is back to 14, right?
Yes, you're quite right.
Okay. Okay. Yeah. Got it. Okay. Oh, that's great. At least now I know the simple mathematics. It has come quite a lot.
Yeah.
And
Yes,
there is like a final bit. If you add stride, you should divide the final dimensions by stride. So for example, if we have padding same, but we add stride 2, then we will end up with 7 by 7.
Yeah.
Okay. Okay. And if we do the stride of 3, then it's going to be 14 by 3. And then would it round to the least number?
That would then
remember how would it round exactly.
That may have an impact on what padding you would need as well.
Okay.
Because the stride would push maybe some extra padding to be added.
Okay.
Yeah.
Okay. Yeah, makes sense.
Okay, so in other words, so here, for instance, in other words, the fully connected network will process the whole image only once, and it will output an 8 by 8 grid for each cell containing 10 numbers. Yeah, so yeah, that's fine. I mean, convolutional networks do process the image only once, but obviously, depending on how many channels there are, they will look at that image, that many channels at the front. And yeah, so this is kind of like a picture of what he's done here. So where it was originally a 7 by 7, because you did a convolution 7 by 7 valid, it just made it into a stack of 1 by 1s, or 10 of them, because that's what you said you wanted 10. And if you're doing the same convolution, but the image is now doubled in size, then just like we said here before, you still get, because you said you want 10 channels, you've got 10 of these guys, but each one of them is 8 by 8. And what he's saying is that each 8 by 8, so imagine if you could, like in the top left-hand corner, there's like a cell there. So each cell has got 10 numbers in it, basically, in the depth-wise. So the idea is that, basically, you've got an 8 by 8 and a depth of 10 as well. So that's how many. So potentially you could be classifying 64 objects, I guess, there, because one object needed these 10 numbers. And now you've got potentially 64 of them in that region. Is that okay, guys? Or
no.
Did I?
No. So I missed that. What do you? I thought we have the number of classes. They won't change, even if the feature map goes up and down. What do you mean by 64? 64. When you say 64.
64 bounding boxes, and obviously each one. So the idea is that you could, there was 10 classes here.
Mm-hmm.
Although what was that in that one? Because that had 10 numbers in it, but was that actually only one object? I can't quite remember as to what that one was detecting when it had 10 in there. So let's have a look. So it had 7 by 7. So to understand, let's have a look. 200 Newton. Now let's see what happens if you replace the dense layer. So it outputs 100 feature maps.
Yeah.
So what was this thing doing? In other words, perform the difference dense layer. Okay, let's have a look. So, okay, here you go. For example, suppose we'd already trained for flower grass. It was trained on 224 by 221 images, and it outputs 10 numbers. Outputs 0 to 4 are sent through as the softmax activation function, and this gives the class probabilities. Output 5 is sent through as the logistic activation function. 6 and 9 do not use any activation. They represent the bounding boxes, center coordinates, as well as its height and width. We can now convert its dense layers to convolutional layers. Don't even need to, we can just copy the weights from the dense layers to the convolutional layers. Yeah, okay, so we were dealing with this network where it was 4 different objects that were being classified.
Mm-hmm.
So, because the 10 were, 4 were sent through a softmax. 1 was just a logistic activation. We just said the objectness score, whether there was any sort of object in that particular situation or not. And then you also had a banding box. So that's the 10 numbers that you got.
Yeah.
So this particular one, it was potentially classifying 4 different objects, or detecting which of the 4 it was detecting, and a banding box for it. So in theory now here we can detect the same 4 objects, but in 64 different positions in the image, because we've got 64 banding boxes, as well as because basically this one little stack, there's actually 64 of these little stacks now in this kind of in this particular architecture. Does that make sense?
So when we ran the 7 by 7 convolutional on 14 by 14 feature map, we got the 8 by 8 feature map. Okay, so the depth of 8 by 8 has to be 64.
So the depth is 10, because that's the number of channels that we chose. So the number of layers here is 10, which is the same as here. And the idea is that we interpreted these 10 numbers in that way, didn't we? 0 to 4 of them were going to be sent through a softmax to give us like an object, which object was detected. There was an additional one which just had like a probability of an object being detected, and then 4 numbers which were the banding box.
Yeah.
But now we've got 64 of those now, because like if you imagine you chopped the top one up into 8 by 8, then each one of those would have depth of 10.
Okay, yeah.
So yeah, but it's a question of whether or not that you want to interpret it in the same way. I'm trying to interpret it in the same way. I don't know whether you would. It all depends on what you do with the data. I mean, this is what I was saying was, okay, fine. The network is not whinging. The same convolutional architecture. Initially, you gave it a 224 by 224 image, and it gave you a 1 by 1 set of feature maps. You gave it a bigger image, and it still sort of happily processed everything. It just gave you an 8 by 8 feature map. And it's all a question of how you interpret what you get now. The two outputs are not exactly identical, because the original was bigger. You've gotten more data here now. Maybe you need to do some more processing later on. But yeah.
Okay, yeah, and one of the things which he mentioned is, I think these YOLO papers quite nice to read, so I think it's a good idea to read them.
Yeah, I was having a look at a Medium post on it. Unfortunately, there's quite a few YOLOs now. Yeah, so there's a little description of it. It apparently, it's extremely efficient. They can do it in real time, apparently, which is like
if you
amazing,
click on the
really.
demo, I looked at the demo. It's a YouTube video.
Yeah.
And especially a YouTube video, the Redmonds demo, and then it's the demo on the live traffic.
Yeah,
and it's very efficient. Like it's separating out everything quite clearly.
Yeah.
I think 1 or 2 cases where it calls a camel as a dog or a cow. It's a good example, yeah.
Okay, so let's have a look at this. So it says, YOLO is an extremely fast and accurate object detection architecture proposed by Joseph Redman in 2015 and subsequently improved in 2016 and 2018. It is so fast they can run in real time on a video as seen in Redman's demo. YOLO v3's architecture is quite similar to the one we just discussed, but with a few important differences. Okay, so let's have a look at it. It outputs 5 banding boxes for each grid cell instead of just 1. So in grid cell, I'm thinking they're probably thinking here, like that 8 by 8. There were 64 grid cells we imagined, and so I guess the depth here is a lot bigger than 10 because they're outputting 5 banding boxes for each grid cell instead of just 1. Each banding box comes with an objectness score. It also outputs 20 class probabilities per grid cell, as it was trained on the Pascal walk dataset, which contains 20 classes. That's a total of 45 numbers per grid cell. 5 banding boxes each with 4 coordinates, plus 5 object scores, plus 20 class probabilities. Yeah, so instead of 10 channels, we've got 45 instead. And instead of predicting the absolute coordinates of the banding box centers, YOLO v3 predicts an offset relative to the coordinates of the grid cell, where 00 means the top left of that cell and 11 means the bottom right. For each grid cell, YOLO v3 is trained to predict only bounding boxes whose center lies in that cell, but the box itself generally extends well beyond the grid cell. YOLO v3 applies the logistic activation function to the bounding box coordinates to ensure they remain in the 0 to 1 range. Before training the neural net, YOLO v3 finds 5 representative bounding box dimensions called anchor boxes or bounding box priors. It does this by applying the k-means algorithm to the height and width of the training set bounding boxes. For example, if the training image contains many pedestrians, then one of the anchor boxes will likely have the dimensions of a typical pedestrian. Then when the neural net predicts 5 bounding boxes per grid cell, it actually predicts how much to rescale each of the anchor boxes. For example, suppose one anchor box is 100 pixels tall and 50 pixels wide, and the network predicts there's a vertical rescaling factor of 1.5 and a horizontal rescaling of 0.9 for one of the grid cells. This will result in a predicted bounding box of size 150 by 45 pixels. To be more precise, for each grid cell and each anchor box, the network predicts the log of the vertical and horizontal rescaling factors. Having these priors makes the network more likely to predict bounding boxes of appropriate dimensions, and it also speeds up training because it will be more quickly learn what reasonable bounding boxes look like. The network is trained using images of different scales. Every few batches during training, the network randomly chooses a new image dimension from 330 to 608 by 608 pixels. This allows the network to learn to detect objects at different scales. Moreover, it makes it possible to use YOLO v3 at different scales. The smaller scale will be less accurate but faster than the larger scale, so you can choose the right trade-off for your use case. Yeah, I must confess I don't really understand this YOLO architecture. I had hoped to spend some time in it. I don't know if the guys are going to go through YOLO. I know they're going to do EfficientNet and one of the other ones, but I don't know if anybody's willing to go through YOLO.
No, so I think they may have, I'm not sure. I think the image segmentation I saw the last part. They may have quickly gone through it already, so there is no detail. Nobody's going into a detail into it. So what they are planning to go through is ResNet in a very detailed ResNet from the Fast AI. Half the lecture, like the whole of the Sunday, was done on it, but
right.
they managed to finish half of the chapter. So
right.
half the chapter they're gonna do today, and the guy who was supposed to take the end of this chapter, I think it's from the I think maybe a semantic segmentation, all the way to the end of the chapter. He's not going to be there, so it's maybe hanging to Sunday. But on a Sunday, somebody else is doing a retina, and there is another one, efficient network. So Sunday, I think they're going to do those two. So this chapter probably they're going to do next Wednesday, I guess.
Right. Okay.
If they don't squeeze this today, maybe end of the rest next.
Okay. I mean, if we still got next week, maybe I'll see if I can find something on YOLO, maybe on Medium, and we'll go through that.
Yeah.
Okay.
There are great videos from Andrew N.
Okay.
This Coursera guy, and they are somewhat outdated by now, I think, if they didn't update that. But he has like a very concise explanation of YOLO.
Okay.
Deep learning course.
Okay. I don't know if you can put in the Slack any references you have to that, and maybe I can have a look at it and see if we can go
I'll
through that.
find links and share it.
Okay. So let's have a look. The mean average precision. A very common metric used in object detection tasks is the mean average precision. Mean average sounds a bit redundant, doesn't it? To understand this metric, let's go back to the two classification metrics, precision and recall. Remember the trade-off, the higher the recall, the lower precision. You can visualize this as a precision recall curve. To summarize this curve into a single number, we could compute its area under the curve. But note that the precision recall curve may contain a few sections where precision actually goes up when the recall increases, especially in low recall values. Motivation for the MAP. Yeah, so this is kind of yeah, so what they do is different levels of precision and recall. They compute the average and then they use the average to report on it instead of just as a single precision recall number. I must confess I didn't fully understand this metric. I kind of got the gist of it. Yeah, that it was something to do with the average of at the recall at different levels of precision. I don't know if any of you guys had any better luck trying to understand what this metric was.
I mean, like, I read through it. So what my understanding is that he says you don't want to sacrifice the precision. So what he was saying is you calculate, I think, precision for 0%, 5%, 10%, 20% recall, and then you average it out. So that's all he's saying. So he's saying take the best precision rather than taking a one precision. Let's say if you have, I think, example here he's giving, like, suppose the classifier has a 90% precision at a 10% recall, but 96% precision at a 20% recall. There is really no trade-off. So it simply makes more sense to use the classifier at a 20% recall rather than at 10% recall, as you will get both higher recalls and a higher precision. Fine. So instead of looking at a precision at a 10% recall, we should really be looking at the maximum precision that the classifier can offer at least at 10% recall. It would be a 96%, not a 90%. Therefore, one way to get a fair idea of a model's performance is to compute the maximum precision you get with at least 0% recall, then 10% recall, and 20% recall, and then so on up to 100%, and then calculate the mean of these maximum precisions.
Yeah,
this is called the mean precision metric. So rather than doing just once, he's saying take it for different threshold of a recall, and then you average out the precision, and that's your good metric.
Yeah, that makes sense. I might have to read up on exactly I can sort of understand as to what exactly the impact of this is on the different algorithms. Okay.
There is in this chapter he has given quite a lot, but it's quite a small. I think there should have been 3 chapters at least.
Yeah, he's covered a lot. I mean, you're quite right. The convolutional networks are so important. He could have afforded to spend more time on it.
Exactly. Yeah.
Okay, so maybe we'll just quickly have a look at semantic segmentation before we finish. So in semantic segmentation, each pixel is classified according to the class of the object it belongs to. For example, road, car, pedestrian, building, etc., as shown in figure 1426. So here, individual pixels are being classified rather than bounding boxes. Okay. So, for example, all the bicycles on the right side of the segment image end up as one big lump of pixels. The main difficulty in this task is that when the image goes through a regular convolutional network, they gradually lose their spatial resolution due to the layers with strides greater than 1. So a regular CNN may end up knowing that there's a person somewhere in the bottom left of the image, but it will not be much more precise than that. Do you guys kind of get an idea of what problem they're sort of describing there? That the way we normally use convolutional networks is obviously you start with, say, a fairly large image, like 224 by 224, and the convolutions over a period of time using strides greater than 1 reduce the spatial dimension, lower and lower and lower. And normally convolutional networks never actually increase the dimension. They really virtually always lower it. And the problem then is that that's not very good for actually predicting or classifying individual pixels in the image, because so much information has been lost. Does that make sense?
Yeah.
Yeah. Because it might be that by the end you've ended up with a 7 by 7 image when you started with a 224 by 224. So the proposal is that, okay, fine, we've gotten a convolutional network. It's compressed the image down to 7 by 7. What if we did upsampling? So that from the 7 by 7, we actually expanded it now So let's say if it was compressed by 32 times by the convolutional network on the way down, we now multiply by 32 on the way out by upsampling it. And there's a few different ways of upsampling it that we can do. Using interpolation and this transpose convolutional layer, which is basically you add in 0 rows and 0 columns, and then you apply a convolution on top of that with a stride of 1, which is not going to change the size of it now, but it will kind of fidget all the data. And the idea is that because you're going to train this network end to end, that interpolation will be its weights will be learned sufficiently so that you can actually do the segmentation. And you guys kind of get that idea, which is where this sort of this expansion, this upsampling is occurring, and this transpose convolutional layer, which is adding additional rows of zeros and zeros in the image, which is then applying a convolution on. But the weights of all that are going to be learned, so that actually you can still use it to classify images. Does that make sense?
Yeah.
Yeah. And then obviously what they're saying, well, okay, that's all very well when you do this, but the problem is that you have lost information basically by the compression that came in, and then expansion. There's only a certain level of accuracy that you can get by just purely doing this. And so what the guys have done, and this is they've actually got sort of skip connections. Actually, yeah, we'll come back to that section. So the solution is okay, but it's still too imprecise. To do better, the authors added skip connections for some of the lower layers. For example, they upsample the output image by a factor of 2 instead of 32, and then they added the output of a lower layer that had this double resolution. Then they upsampled the result by a further factor of 16, leading to a total upsampling of 32. So the idea is you upsample it only a little bit, and then add in some data from earlier on, and then you upsample that to be again. And then that gives you better performance. And then if you do that a second time, where maybe you've got a second skip connection as well, which gets you even more info on the upsampling, when you're upsampling, then you can get better performance. So this is basically the overall architecture, which is you've got you've got feature maps, you've downsampled it, then you do upsampling, you get a skip connection which adds in some data from earlier on, and then you do some more upsampling, which gives you the final result. And the idea is that in this way, you've not only got done the object detection bit that's going on here, but you've actually kept some of the original features here, which help you to classify the actual individual pixels. Does that make sense?
Yeah. So in a sense, what he's trying to say is when we upsample, then it can easily define those, like if you go up an image where it's saying a people or a car, then each pixel, like it, because we upsample it, so what does it mean? Like it can draw the people properly? Because
well, the way we train it is that we actually tell it, don't we? We classify each pixel in the image as to whether or not it's it's a person or it's a car or a bike or whatever.
What's the advantage of upsampling it then?
Well, you have to upsample it because if you use the well, it's all assuming that you use the convolutional network in the first place, that you downsampled it initially, because that's what your original network did, and then you upsampled it back. I wonder what would happen if, I guess you don't want to keep the original. I can't imagine how you would do it if you didn't do this downsampling and then upsampling, because let's say your original image was by 224 by 224. If the only convolutions you ever did kept that size because the stride was always 1, and then you could have a number of these different guys, and then eventually you had your final image. I don't know if that would train as well. Somehow, obviously, what this guy is doing is keeping some of the original features from the earlier on, but also some of this kind of detection of features within the regions, that a combination of both of those two is giving you better results than just going from here to over here. But I haven't seen an explanation of what would happen if you just went from here to over here, you know, doing something, you know, without all this down and up.
Connected with computational overhead, which adds, like, if you want to go from big image to big image, but still learn a lot of fine-grained features, it would be computationally more expensive than going down and then up in size.
Yeah, it could be. It could be. Or the fact that you're going down maybe just gets you to really learn features that are important, and maybe, you know, without that, you know, it's just, the performance will just not be as good. But yeah, it's interesting. So that's semantic segmentation basically. And then he's got a nice kind of blur, you know, advert for computer vision to work on it, because really exciting things are happening. Yes, so TensorFlow's got a couple of interesting functions. So there's convolution. I mean, so far we've been looking at 2D convolutions, which are more suited to images. But you've also got 1D convolutions, which would be more suitable to stuff to do with natural language, I guess, because a lot of those are one-dimensional vectors and don't really work well as two-dimensional objects. And there's also convolutional 3D, which can be applied to 3D images, I guess. I don't know if there's I mean, here's PET scans is specifically mentioned. I don't know if there's a format for 3D images. There's a dilation rate. This is what's used to do the that upsampling, which is where you can take a particular shaped filter and then increase it by adding in additional zeros. So this lets the convolution layer have a larger receptive field at no computational price and using no extra parameters. And then there's a depth-wise convolution as well. So all the ones we're looking for so far were operating on a particular channel, but you can work across the convolutions across the depth layers rather than across the particular across just the height and width of the image. And that's pretty much it in terms of this chapter. As I say, YOLO, I think, you know, yeah, if we get time, let's do it next week, because it's really quite an important network, and I would be quite interested to know exactly how it works.
Yeah, and then just a couple of things about those, you know, 1D, 2D, and 3D convolutional networks. You know, the blog you mentioned, what's the name of the guy?
Kunlun Bai.
Yeah, so that's very good to understand all these kinds of how they work. So very good explanation over there. And in addition,
okay.
Yeah.
What do you guys think about doing that next week? I mean, I haven't read it yet, so I think it looks like you've read it. I don't know if any of the others have read it. So if you do YOLO, which might only take half an hour, and do the other one for half an hour.
Yeah, I think that makes perfect sense. Yeah.
Okay. Great, guys. And yeah, thanks. So I think I'll let you go because it's almost 8 o'clock now.
Absolutely. That's great. Thank you very much. Thanks for your time, Arshad. I appreciate it.
Okay, thanks.